good morning or good afternoon, I guess whatever time you guys are watching this. Welcome to the SNIA Storage Developer Conference. I'm John Michael Hans from Intel. I'm a Senior Product Manager and Strategic Planner for the Intel Data Center SSDs. I also co-chair the NVMe Express Marketing Work Group and the SNIA SSD Special Interest Group.
And I'm Bill Martin from Samsung. I am the co-chair of the SNIA Technical Council. I am on the NVMe Board of Directors, and I co-chair a couple of groups within both SNIA and NVMe. So today, John Michael and I are planning to do an NVMe 2.0 specification preview of what we're doing with 2.0 and where we're going. So take it away, John Michael.
Thanks, Bill. All right, so NVMe Express Technical Specification Roadmap. So today, this is the actual NVMe roadmap. So today in NVMe Express, we have three different specifications. We have the NVMe Express specification, which you can think about that as kind of the standard for PCI Express solid-state drives. And the current standard as of today is NVMe 1.4. And some of the major features that were included in NVMe 1.4 were NVM sets, and along that with the ability to do something called I/O determinism, or the ability to actually physically separate data placement of actual data within an NVM on a specific device, mainly across channels or an NDI, to get really good quality of service. And the I/O determinism, you have this thing called persistent latency mode that allows you to basically coordinate the host to device, garbage collection and background operations. And so there's some good stuff in NVMe 1.4. The persistent event log was one of the other major features, which allows kind of a black box recorder for the SSD to record all major events and timestamp them, and then rebuild assist. We actually talked quite a bit about these in a recent webcast that Bill and I did on NVMe error management and reporting and logging. So definitely go check that out if you guys missed it. But so we're not here today. We're here to talk about NVMe 2.0. So I mentioned really we have today these three NVMe specifications. So NVMe, again, which is PCIe solid-state drives, NVMe were fabrics, which took basically the core principles of NVMe Express and then allows you to use that transfer over networked fabrics like Ethernet or Fiber Channel or InfiniBand. And that the latest specification is NVMe over Fabric 1.1. And then you have the NVMe Management Interface specification, which is all about management of NVMe devices in band and out of band. So out of band meaning agnostic to the operating system. And so here, NVMe 2.0, this, you can see the left edge of this is to the right edge of this is kind of the scheduled time. I think realistically, we're kind of looking like end of Q4, early Q1 for the NVMe 2.0 release. It just basically is a matter of when the work group gets everything standardized and reviewed and put together. And Bill and I are going to talk a lot about today, just specifically what does this mean. And it's not like NVMe 2.0 is going to mean that all NVMe before it was not compatible anymore. Really, the whole 2.0 push is really we're kind of re-architecting the way that we view the NVMe specification. And I'll talk a little bit more about what's going into it. But really 2.0, think about 2.0. The major thing that we're doing is kind of refactoring the specification. And so now it's not going to be these three specifications anymore. The NVMe MI spec will still kind of live. But one of the things we're doing is specifically specifying out the transport specifications, so removing PCIe from the base specification and putting it into its own transport specifications, and we're changing the way the command sets work. So today you have basically your block IO command set or standard command set for LBA access, and there are new command set accesses that we're going to talk about today, mostly being zone namespaces, which are really good for kind of large capacity SSDs to reduce write amp and kind of force sequential writing into smaller zones. And then the other specification is key value, and this allows you to actually have a native key value command set for retrieving and getting objects. And really the big change, right, is this is a pretty massive overhaul of the spec, which is why we're calling it NVMe 2.0. We're merging it with the fabric specification. And of course, these namespace types allow you to have a SSD or NVM device that actually supports different namespace types and namespace commands in different command sets. And so the way we think about this, the way our process is in NVMe Express is we have different technical proposals that get approved, and some of these might be enhancements to current features. Some of them are further clarification of specific features, and then some of them are the new features themselves. And the way NVMe refers to these internally before they're in an official specification is a technical proposal. So when you see a TP and a number, That's kind of what we mean. And so there's just some of the stuff that's been ratified in the 1.4 specification are further events for persistent event log to continue the making persistent event log more useful by logging new events. ANA-based protocols with the asymmetrical namespace access, and then the namespace write protect, some optimization. The C is basically just saying they've updated this technical proposal to make it more clear and the implementation more specific. And today we're going to talk about some of the enhancements. These are new new commands, and again, we're going to talk a couple about these today. We're going to talk about endurance group management and simple copy command specifically, and then there's some cleanups on the controller memory buffer. But I'm going to talk about those in a couple different slides. And then for the enhancements, again, I just mentioned some of these which are basically cleanups. The telemetry enhancements were basically required implementation if the host initiated telemetry has a scope of the NVM subsystem. For the non-data transfer, non-MDTS, that just adds a limit to the commands that affect the LBA without the host to controller data transfer. And so a lot of these are just not more quality of life kind of fixes. These aren't, major overhauls or implementations, but really just being more clear. And again, that's part of the process as the NVMe spec continues to mature. For all the features that are getting actively used, we want to make sure that we're clarifying them and being very specific about how they operate, so that and again, once people start implementing commands and actual NVMe features, then we start getting feedback on, hey, this worked, this didn't work, this was not clear in the specification, and that's part of when you see some of these optimizations. So the ones in blue, some of these have actually been ratified. They're just not posted to the public NVMe Express site. But for the black ones, the way that NVMe currently rolls out features is once they get ratified and have passed member review, we actually post them to nvmeexpress.org in the ratified TP section. And that way people can actually start looking at what's a preview of the new specification prior to the new spec coming out for features that are really ratified. And again, the way I'm a product manager, the way I have a lot of my engineering team and product teams working on features is once they get ratified, then we really do the full scoping. Now, for some major big features like what Bill is going to talk about, like zone namespaces and key value, that those require quite a bit more planning, right? Where you need controller interaction and major firmware overhauls about the way devices work. Those, again, we suggest you become an NVMe member, because if you're an NVMe member, you can go to the nvmeexpress.org website in the members section and actually download the work in progress drafts of all these specs being created. And of course, these are the actual major features that are going to make it in. Besides, Bill is going to talk quite a bit about the refactoring, about how that actual spec looks when we put it back all together. But the ones I'm going to talk about today are simple copy command and command group control. And then Bill is going to walk you through key per IO, namespace types, zone namespaces, and key value. And again, these are the major new things that are coming in the next generation NVMe 2.0. So simple copy command, basically it's kind of surprising that this command didn't exist before, but it makes sense, right? When you write to data to SSDs today, you're writing to a logical LBA. Generally, in the device side, we have something called a flash translation layer. That's usually a map in DRAM of the logical LBAs to host physical addresses, and that's physical addresses on the NAND. And then you have a maps to a host LBA, and generally, the host LBA, the actual data underneath it may change if the drive is doing wear leveling or garbage collection or whatnot. But sometimes for some applications, you actually may want the data to be contiguous. If you have data that's sequentially written, once you invalidate all that data, if it's all together in the same erase block, then it's good for the garbage collection algorithms, because then you can go, basically you don't have to move as much valid data from that erase block to another place on the SSD, prior to you doing the garbage collection. So this simple copy command just allows you to say, hey, these are a range of LBAs from different ranges of LBAs, and you want to map them to a contiguous range of LBAs in the destination. And so think about this as kind of like a defragmentation. You could do some really nice swizzling on the drive, but this allows you for the host to not have to be interacted. So the host doesn't have to copy the data into memory, host memory, and back to do all the actual reads and writes across the PCIe bus. This command, you can just specify the LBAs that need to move, and then the SSD internally can actually move the data around, or just change the basically our mapping, right? Again, I mentioned SSDs do this mapping in the logical to physical through this flash translation layer. The SSD can just basically change the mapping without having to change the physical placement of the data, or they could actually change the physical placement of the data if that was better. If the SSD knows, hey, all this data is chunked together in a certain LBA range, it could. And so this, and again, this expands to farther than bigger than SSDs if you have an NVM subsystem that is much bigger than a single SSD. This could also be good, right? If you have SSDs within a topology that want to copy data to another without having to go all the way back to the host, in some topologies, this might be a way to do that. And so, this, again, NVMe Express doesn't specify why these commands are used. That's kind of up to the implementer, but this is a new feature that allows for some cool flexibility. The next feature I'm going to talk about is command group control. This is TP4046. At one point, this was helped standardized by Dell EMC, and they called it lockdown for some time. So if you hear lockdown, that might be also the terminology that they referred to this command group control. But if you think about an OEM system, like for instance Dell, that sells a server that may be used on Windows, it may be used on Linux or VMware, they want a standard management set, which is why they use out-of-band management through NVMe, but they also want to prevent from people doing stupid stuff. Like, so with in-band, if anybody knows about NVMe Express or NVMe CLI, it's basically a command line interface, in the admin queue that talks directly to the admin queue in Linux, and you can send any single command you can possibly think of to the device. And so I can send a format command and instantly wipe all the data on a drive. And there's some OEM customers that said, hey, that's kind of scary. Maybe we should lock down some commands. And so the idea is that you can use the out-of-band mechanism, or having like a management console for a system or a server actually send out-of-band commands to basically restrict the execution of specific commands. And so there may be commands like, for instance, security send and receive, to be able to set a locking range through Opal, or set an encryption key on the drive. Maybe you don't want your customers doing that. Maybe you want to only own that by the system management console and the BMC firmware. Or maybe, like I mentioned in the use case of like a formatter or sanitize command, well, maybe you don't want the user to accidentally wipe their data. And by the way, Microsoft does something similar to this in the Windows OS. They have ioctls to basically talk from the actual admin commands down, basically how you send commands to the devices, through an ioctl, and then the Microsoft driver filters out things that might be kind of bad. And then they only allow you to do specific low-level stuff in like the PE environment. So I think about this is just very similar to that, but just at an NVMe level, you could be able to unlock and lock certain commands. And then, this is the one, I'm going to pass it off to Bill here in a sec, but I'm just going to say a few words about the refactoring, and then I'm going to hand it over to Bill to walk us through this. But really, the idea of the refactoring is, hey, there's a lot of stuff going on in NVMe, and we don't want to, one, slow down innovation, because innovation's been key to NVMe's success and continuing to innovate on all the new features and development that we've been doing. But going back to the core values of fast, simple, scalable. So think, for instance, if you're an SSD vendor that makes a consumer SSD, all you really care about is the performance and then the PCIe low power features, because you want to have good battery life. You don't maybe care about all these brand new features that are getting added to NVMe Express, like zone namespaces and key value and all this stuff that's very data center specific. So we want to continue the innovation, without slowing people down that currently have products. And a good way to do that is to completely refactor the specs. So having modularity for all these new command sets and new functionality will be able to allow innovation to happen while we continue to have the core specification for all the stuff that's not going to change, right? The core stuff about NVMe, like the queuing mechanism, the command set, the log pages, a lot of the stuff that is just core to the spec is now going to be in the base specification. And that's kind of the biggest change, right? Is shoving some of the stuff that was in the fabric spec into the base spec, and then the biggest change is pulling out the PCIe transport away from the PCIe NVMe base specification into its own specification. So with that, I'm going to hand it over to Bill to kind of walk you guys through what exactly is going on.
Okay, thanks, John Michael. So looking at this a little bit more in depth, up at the top left side of your screen, you will see the current NVMe specification layout. So we have NVMe-MI, which is the management interface spec. We have the base spec, and currently the base spec includes the base architecture, but it also includes the mechanisms for moving things across the PCIe bus, and it also includes the entire NVM command set, which is the basic logical block addressing command set. And then we have another spec that is the NVMe over Fabric specification. So the first thing that we're doing as we refactor is we're looking at cutting the pie a little bit differently. The management interface spec is staying as is. We're not making any changes to that. However, the base specification, we're doing a couple of things. We're taking some things out, we're putting some things in. The first thing we're doing is we are taking out the things that are specific to the NVM command set, which is your basic block IO command set. That's going to move out of the base spec, as you see down here at the bottom, into a separate command specification. We are also pulling in things from the Fabrics specification that are specifically related to how you would talk to any fabric. And fabrics are a packet-oriented transfer as opposed to PCIe is a memory-based transfer. So the base specification will still have things that talk about memory-based or packet-based transfers, but they won't have the specifics of a given transport protocol. So we're then taking out of the base spec the items that are specific to the PCIe transport protocol. And we are creating separate specifications, one for the PCIe transport mapping, one for an RDMA transport mapping, one for a TCP transport mapping. And then in addition to that, over the last year plus, we have worked on zone namespaces, as John Michael referenced, and key value. And I'll get a little bit more into those. So the outcome is we will still have a management spec. We will have a base specification that has more of an architectural overview and some of the things that are necessary no matter which command set or which transport you're using. We will then have 3 transport specifications, and we will end up currently with 3 command set specifications. By doing this, it allows us to more effectively move forward with enhancements to the specification. John Michael, I'm going to have to ask you to advance the slides for me. So the new specs kind of covered these a little bit already. The NVMe IO command set specifications that we will have the NVM command set, and that source is from the existing NVMe 1.4 base specification. We will have the zoned namespace command set. The source of that is Technical Proposal 4053. That has been through member review. That is ratified. There is a ratified version of that available for you to look at on the NVMe site. We will have the key value command set, which is Technical Proposal 4015. Again, that has been through member review. That has been ratified and is available on the NVMe site. So those will be the 3 command set specifications that we have. We will have 3 transport command set specifications, which will be the PCIe transport. The source of that is material that is currently in NVMe 1.4 base specification. There will be no changes to the material that is there. It will simply be putting it into a separate document. And that is part of what John Michael talked about earlier, where he said that we're not making a change that is really changing how your device operates. We are changing how the specs are done so that you can enhance them with future features more easily. We'll then have the RDMA transport and the TCP transport. Both of those are coming directly out of the NVMe-oF 1.1 specification and will not change anything that was in the 1.1 specification, but simply reorder how they are done. Next slide. So what are the changes with the base specification? So on the base specification, the fabric specification, portions of it will be integrated into the base spec. So that will be what you see down here of the message and message-based transports. That portion of it that can be isolated to just the messages that need to go will be pulled into the base spec. The base specification will have a theory of operation section that is enhanced with two new concepts, domains, endurance groups, NVM sets, and namespaces will be within that. And then it will have a memory-based theory of operation and a message-based theory of operation. That will talk about how those interfaces work within the NVMe architecture, but will not talk about the specific protocol necessary for the underlying transport. So in other words, it will not talk about the specific PCIe registers that you're using. That would be in the PCIe transport specification. We have created an NVM Express architecture section. That is something that was really kind of distributed throughout the existing spec. That's been pulled together into more of an architecture section. PCI registers and concepts, again, I've said, will be moved to a PCIe transport specification. We've improved the organization of the controller portion of the spec. We have architecture, data structures, and features. The data structure section, again, it's been reorganized to only cover data structures and not the concepts. So the concepts will be in the architecture and the data structures will just contain the data structure. So we've tried to bring things together in a way that for a new implementer who hasn't been living and breathing this for the last 5+ years or more, that they will be able to pick up the spec, understand the spec, and go through it. Next slide. So the architecture section, it's going to be earlier in the document to set context for the reader. The current NVMe specification, the architecture section, is way down towards the end as opposed to at the beginning. Within it, we will have these basic categories that we will have. We'll have the NVM controller architecture, which will include a controller model and the controller types and controller properties. We'll have subsystem entities, which will include namespaces, NVM sets, endurance groups, and also not listed here will be domains, which I'll cover later in this presentation. We'll have another section that is on the NVM queue models. The queue models are consistent across all of the command sets. So that is something that we're defining in the base spec. Command architecture will talk about overarching command architecture that is necessary for both administrative commands, which will be covered in the base spec, as well as I/O commands that are included in each I/O command set. So this will cover things like command ordering, fused operations. So if your command set uses fused operations, how fused operations work will still be in the base spec so that everyone does them the same. atomic operations, and command arbitration, how you arbitrate for what you're doing. All of that will be, again, in the base spec. Controller initialization and shutdown. This is an overarching principle that applies to administrative commands as well as I/O commands and is independent of the transport protocol that you're using, and therefore that will be in the base specification. We will include sections for reset types, keep alive, privileged action, and firmware updates. As again, these are all overarching principles that apply to any command set. Next slide. So where are we at in executing this plan? We've done quite a bit of work. The check marks are things that we actually have completed as part of the reorganization. The open boxes are things that we are currently working on. So we have created the outline. We have integrated the fabric spec back into the base spec in terms of the things that are not transport protocol specific. We have done the reorganization for better readability and flow. We have added coverage of missing topics in the theory of operations section. One of the things is we added new features to NVMe over time. A lot of the theory of operation for those features was hidden down in the actual commands. That's been pulled out and put together into the theory of operations section, covering all things that need to be there. We created a separate fabrics transport template, and from that have created the three three transport specifications, one for PCIe, one for RDMA, and one for TCP. Generating the command set specifications, we are working on that. We have created a command set specification template. We have created an NVM command set specification. And we are at the point right now where these individual specifications that we've broken out are being brought to the overall technical work group within NVMe to review them and make certain that what we did was simply reorganize things, not modify any functional meaning as we've done this. So we're just getting started on that validation process for these things, but the NVM command set specification is written and ready for validation. Create the initial ZNS and KV command set specs based on their TPs and command set templates. The ZNS spec, the editor of that, has been doing a good job of following the developments as we work on the template, and that has been a back and forth to help improve the template for other command sets. So that is close to completion. The KV command set, we're kind of waiting to allow the rest of this to get completed before rolling the technical proposal that generated the KV command set into the new template. But again, this is not changing any functionality whatsoever. Integrate namespace types. That was critical to completing this refactoring because namespace types, which actually is now misnamed because we changed what we were doing midstream. This is really a multiple command set proposal, and it is the functionality that needed to be added to NVMe to allow for multiple command sets. So that has been integrated into the base specification. So we are very close to starting this generate final set of NVMe specifications, including everything we've just talked about, the base spec, the transport specs, there are 3 of them, the command set specifications, which are 3 of them. Once we have all of those completed, then we will integrate all ratified technical proposals into appropriate specifications. And finally, when we get done with all of this, we will align the release of all of these to a new release of NVMe MI 1.2 specification. Next. So what did it take to enable multiple command sets? What we had to do was we created a new field within all of the commands that is a command set identifier. But we had this question of, when you have multiple command sets, which command sets can operate on a controller at the same time? So we have created a data structure that provides up to 512 different combinations of command sets that could be supported. Right now, we only have 3 command sets available, so there are much fewer than 511 possible combinations. But what this diagram is showing, you'll notice that there are color codings for the command sets. And so controller 0 is only able to support 1 command set at a time. And it is currently configured to only support command set number 2. It can be reconfigured to support a different command set. However, if there are any namespaces currently attached to it that have a command set associated with them that is not supported in the new combination, you cannot switch to that combination. So something I said there brings up another point, which is command sets are associated with a namespace. A given namespace is associated with one and only one command set. It can be associated with no command sets, which makes it an administrative namespace. But if it's associated with a command set, it's associated with one and only one. Okay. In this diagram, controller number 1 is like controller 0, where it's only associated with one command set. Controller number 2, in this example, supports 2 different I/O command sets. It supports I/O command set 1 and I/O command set 2. So it can have 2 different namespaces attached to it, each of them with a different command set. And controller number 3 supports all 3 I/O command sets and has 3 different namespaces attached, each of those namespaces associated with a different command set. So that gives us the basis for how we move forward with supporting multiple command sets and specifying the capabilities of the controller as to which command sets it can support and in what combinations. Next. So I/O command interpretation, we have in the base specification a common command format, which has a command identifier. That's actually command set so there's a command identifier and then an opcode within that command. Those are common for all I/O command sets, for all I/O commands. There is a field that indicates whether or not your data pointer is an SGL or is a another pointer to data, and then it has a bit or 2 bits actually that indicate how fused commands or which portion of a fused command operation you are in. So the new addition to this, all of that in command D word 0 was in the base spec already. The new addition is command data word 1 was previously a reserved word, and we have put a namespace identifier in there. Or sorry, back that up. Namespace identifier has been there all along. Namespace identifier associates what namespace this command is going to. Through that namespace identifier, you have identified a command set. So by doing that, you get to a command set which determines how you interpret this command. Couple of notes here. If you are in command set identifier 1, a command may mean one thing. In command set identifier 2, that same command identifier and opcode may actually refer to a different functionality. What we are attempting to do as we overlap these is to make certain that it is comparable functionality. And I will throw it out here, we'll explain it more later. For example, in the NVM command set, you have a read command that has a particular opcode for it. In the key value command set, you have a retrieve command, which has similar functionality, but much different parameters in terms of how you do it. That shares the same opcode with the read command. For commands that have totally new functionality, we are attempting to not overlap the command opcodes between the different command sets. Next slide. Okay, so I'd like to next move into the zone namespace command set. I am going to do a very brief overview of these because there are other SDC presentations that go into great detail. And our point here is not to give you the detail of these, but rather to show you what is being done as we roll out NVMe 2.0. So the zone namespace command set, logical blocks are grouped into zones. They're written sequentially within a zone. There are some additional features that will allow portions of the zone to possibly not be sequential, but that's coming features, and as I said, there are presentations that talk about that within SDC this year. There is a state machine associated with each zone. It controls the operational characteristic of each zone. State transitions may be explicitly controlled by the host, or they may be implicitly controlled by host actions. And you'll see a list of the states over here. We're not going to walk through those in this presentation. What are the benefits? It has the ability, if used appropriately, to reduce write amplification. It can reduce over-provisioning, and it can reduce memory on storage device, in other words, your DRAM. By doing the sequential writes, you can more quickly or easily move data directly into your storage media. So that's kind of a really brief overview of zone namespaces. As I said, I think we have 7 or 8 presentations as part of SDC that talk about zone namespaces, and I would refer you to those to get much more detailed information. Next. The next one is the key value command set. Again, there is a very detailed SDC presentation on key value, so I will not go into a large amount of detail here, but the basic concept is that on key value, instead of addressing your user data based on a logical block address, you address it using a key. This key can be within the current specification, anything from 1 to 16 bytes. The specification does allow that key to grow for future enhancements, but that will require enhancements to the spec. The value can be anything from 0 to 2 to the 32nd minus 1 bytes. So the value can be a very large piece of data. The commands that are being done within the key value command set is we have the store command at the bottom. I'm going to not go in these in the order they're listed. The store command allows you to store a key value to a key value namespace. And it stores it based on the key. The key is a pointer to that data. Retrieve retrieves the value associated with the specified key. So those two are kind of the equivalent of write and read in existing logical block addressing functionality. You have the ability to delete a key and value associated with that specified key. This is the equivalent in a logical block address scheme of doing a deallocate. However, currently deallocate is a recommendation, not a requirement. This actually facilitates the reduction of over-provisioning necessary on your device by allowing you to actually totally get rid of the mapping in your mapping table. You have the ability to list all of the keys that are on the device. This is useful for a variety of reasons, including data recovery if you need to move data from one device to another. And then you have the ability to query to find out whether or not a particular key exists on the device. So just a really brief statement about the value proposition of key value storage. It allows you to store a quantity of user data that is associated with a key that is addressable as a complete quantity. For example, you could store a photo as a single quantity of data. So now when you get to the device and you want to look at that photo from a programming point of view, it's a single address that gives you the information about that entire photo. And you don't have to go find a whole bunch of different logical block addresses and logical blocks that may in turn make up the photo. What this facilitates is the ability to do computation on user data, because your user data is now identified as a complete unit as opposed to a whole bunch of pieces that are each in logical blocks that may or may not be contiguous. So those are some of the advantages or reasons why you might want to use key value storage. And again, I would point you to another presentation at SDC, one that I will be doing that talks about key value in detail, and you can have an entire session learning more about key value. Next. So another feature that has been added to NVMe that will be part of the 2.0 release is domains and partition. So an NVM subsystem may be something much bigger than just your SSD. It may be a warehouse scale storage system. So it may be something where you have a very large amount of storage and it's a lot of different components, but it is still considered an NVM subsystem. So the subsystem may be constructed from multiple domains. So first, let's talk, what is a domain? A domain is the smallest indivisible unit that shares state. For example, it is the unit that shares power state. It is the unit that shares capacity information. These units then can communicate with each other across communication boundaries. So a domain may have 0 or more controllers. It may have 0 or more namespace identifiers. It may have storage or it may not have storage. But what is unique about it is that it is self-contained, so that if there's a failure within it, the fault is isolated to that particular domain. Domains may be added, removed, reconfigured, partitioned, or they may fail as an individual domain. Domains do support endurance groups being able to be created within a shared namespace. So in the diagram here, you'll see several different domains. Domain 1 has 2 fabric controllers, and it has one namespace, namespace A, that is a private namespace. It has another namespace, namespace C, which is a shared namespace, and that namespace is shared with the fabric controllers that are in both domain 3 and domain 5. The storage associated with that namespace, namespace C, is all within domain 1, but it's accessible from other domains. Domain 3 actually has no storage within the domain. It is using storage that is in shared namespaces, which exist in other domains, namely in domain 1, domain 2, and domain 4. Okay, and domain 5 likewise has no storage. It shares the storage capacity that exists in other domains. So domains will be defined in the 2.0 specification as a new architectural element, will be defined in that architecture section. Next. Key per IO is also a new functionality that we are working on. It is Technical Proposal 4055. What this allows, and it is very important to differentiate key per IO and key value storage. The keys in these two different cases are very different things. Key value storage, the key identified where the data was. In key per IO, the key is actually a security key. In key per IO, this allows a unique key to be used on a per IO basis to encrypt or decrypt logical blocks stored in a namespace. The key tag is in the command, and it specifies the encryption key to use. The NVM subsystem supports up to 64,000 keys. So the key itself is stored on the NVM subsystem. The key tag in the command specifies which key to use for this particular IO. Configuring keys and management of key tags will be defined in the TCG, which is a totally separate working group that we have a liaison relationship with in NVMe, but it defines the vast majority of security work that is being done. So that's a really brief overview of key per IO. I am fairly certain that there is also another talk being done at SDC this year that will go into more depth about key per I/O. Next. So endurance groups is a mechanism to break down media into pieces that are in some way physically related to each other. So it is a way to manage your capacity. It allows for creation and deletion of NVM sets, which an NVM set is a portion of memory where if you are in different NVM sets, I/O to those sets will not interact with I/O to another set. So this allows for performance enhancements. It allows creation and deletion of endurance groups. Endurance groups are another way of breaking down the media that help to limit or reduce the amount of write amplification factor you have on the device. And it allows allocation of media units to endurance groups or NVM sets. And you'll notice from the pictures here that an NVM set may be part of an endurance group. So you have both of these pictures showing that an endurance group may contain multiple NVM sets, and the NVM sets in turn contain media units within them. So this is another new feature or functionality that will be in NVMe 2.0. And again, this will be very well defined within the architecture portion of the description of the new base specification. Next slide. So we have completed our time. We have tried to give you a good overview of what is being done to create NVMe 2.0, what some of the new features are, and how it is fully backwards compatible with NVMe 1.4. It is renamed more out of a structuring point of view and not because it's some major shift that's incompatible. So with that, I would like you to take a moment. At the bottom of your screen, you should have the option to rate this session. Your feedback really does matter to us. Both as presenters, we like to know whether we have presented what you want or you'd like to see something different so that we can do something better next time, as well as for SDC as a whole to know what content you as developers are interested in.